Thanks a lot for the introduction. I hope you hear me. I'm Kathlén, and I will tell you about our interdisciplinary work between mathematics and computer vision. This is joint work with Timothy Duff, Anton Lakin, and Tomasz Peidler. Tim, Anton, and I are mathematicians who do algebraic geometry, and Tomasz is our resident expert in computer vision. Our result is a complete list of minimal problems for reconstructing point line configurations in space. And my goal is now to explain in simple terms what exactly that means. So one of the grand challenges in computer vision that motivates our work is reconstructing 3D scenes from many images. This has many applications. For instance, 3D mapping from images taken by drones, or in autonomous driving to localize and navigate cars in the 3D world, or in the movie industry to reconstruct 3D background and for tracking moving cameras and combining real and virtual worlds together. So the underlying task behind all of these applications is to reconstruct 3D scenes from many given 2D images and to also reconstruct the positions of the cameras that took these pictures. This is typically done using the 3D reconstruction pipeline. Here we have given a bunch of images. Then the first step in the pipeline is to take a few of the given images and identify points and lines that they have in common. In this example, a detection algorithm has been used that only identifies points, not lines. In the second step of the pipeline, we forget the original images and only keep the points and lines we have identified. Then we reconstruct the 3D coordinates of those points and lines, and also the camera positions. So in this example, we had identified 5 common red points, and we aim to reconstruct the 5 points in 3 space and the 2 camera positions. Finally, we repeat this process several times until we have recovered all cameras and also enough points and lines to approximate our 3D scene. So in the end, we maybe get some sort of point cloud that we can further process, for instance, to a shaded or textured surface as shown here. So now let me tell you about our result that is a contribution to this second step of the pipeline. Here we forget the pictures and only work with points and lines. So the problem becomes a purely algebraic problem that we can study with techniques from algebraic geometry, which is my area of expertise. So let me show you an example. Maybe the most common reconstruction problem that is used in this pipeline is the 5-point problem. Here, as in the previous slide, we have 2 images that both show 5 points each. And we want to recover the 5 points in 3 space and also the 2 camera positions. So now when we try to do this in practice, we solve a system of polynomial equations, and that typically has 20 solutions, when I also count complex solutions. But this is very nice because among these 20 complex solutions, we can first easily identify which solutions are real, and then also which solutions are feasible in real life. For instance, the recovered 3D points clearly need to lie in front of the cameras, for instance. And that way we can quickly narrow down our solution set and identify the one true solution we were looking for. And all in all, the 5-point problem works nice in practice. Let me show you a problem that is less nice behaved. Here is the 4-point problem, which is really the same as the 5-point problem, just that I'm working with 4 points instead of 5. Now, if we try to solve this reconstruction problem, we will find infinitely many solutions. And having infinitely many solutions is bad because now we will have a hard time to find the one true solution that we actually wanted. Because to get this ground truth solution, we will have to solve an optimization problem over the infinite solution set. And that is a much harder task than checking just 20 possible solutions as in the 5-point problem. And so that is why we do not really want to work with the 4-point problem. Let me show you another example that is also not nice enough. The 6-point problem. Here we have given 6 points in 2 images and we want to recover them in 3 space. However, if I have 2 pictures that both show 6 random points and I try to solve the reconstruction problem, I will not find any solution at all, which is clearly bad. So now you could, of course, maybe argue and say, well, but what if I start from 6 points in 3-dimensional space, and then I take 2 pictures of them? Shouldn't I be able to find a solution to the reconstruction problem since I started from 1? And so this is theoretically correct. However, every time we measure points on given images, there will be error, which means that we always work with noisy data. And the moment our data is noisy and no longer exact, we will not find a solution to the 6-point reconstruction problem. We first have to denoise the data, which is again the harder thing to do than to just work with 20 solutions in the first place. And all of this motivates our definition of what we call a minimal problem. This is the most important definition clearly of this talk. So a minimal problem is a 3D reconstruction problem whose number of solutions is typically finite and positive. And if we look back at the 3 examples we discussed, we see that the 5-point problem is the only minimal one, as it typically has 20 solutions. This leads us to the natural question if we can maybe determine all minimal problems. In other words, is there some sort of catalog that lists all minimal problems, such that I can choose a fitting one for my application, or such I can check if a specific reconstruction problem I encounter is minimal. And secondly, can we compute how many solutions each minimal problem has? This is important for applications because problems with a small number of solutions are expected to be solvable faster in practice. So in that sense, the number of solutions measures the complexity of a minimal problem. And finally, the question is, can we do all of this if we do not only work with points, as in examples before, but also with lines? Because many modern detection algorithms are not only able to detect points that pictures have in common, but also lines. And this is highly important in many applied settings, because you see here, for example, that many architectural structures naturally have a lot of lines in the real world. And so we want to work with them. And we have answered this question with, yes, we can do it, essentially, by providing a complete catalog of minimal problems under the assumption that all points and lines are visible in each given image. So here is a 5-point problem again to understand this assumption better. Here we have, for instance, discussed that we have 2 images, and both images show all of the 5 points. And it's not so that one of the images is missing some of the information. So under the assumption that all the images that we're working with sees all the points and lines, then we have a complete catalog of minimal problems. And here it is. This is our results. We have shown that there is exactly 30 minimal problems, and this table lists them all. Let me show you how to read this table at an example. Down here, we have the 5-point problem. The number 2 of 2 views means that we have 2 given images. The icon in the table shows that what each image sees. In this case, this is 5 points. And then at the bottom, we see always the number of solutions, which was 20 in this case. Let me show you also another example. Here we have a reconstruction problem with 3 images. That's why there's the number 3 here. The icon shows again what each picture sees. In this case, that is 3 points, and 2 of them have a line attached. So this is also what we see in the example. So here's a 3D scene, and then we have 3 pictures. Every picture shows a yellow point at the tail of the dog, a blue point at a corner of the cube, together with a blue line along one of its edges. And then there's also a pink point at the cylinder, together with a pink tangent line. And so this reconstruction problem has 312 solutions, as we also see in the table. And I wanted to show you this problem because I want to point out that our algebraic techniques can not only be used to derive this catalog of minimal problems, but also to develop solvers for each of these minimal problems. And so my co-authors have developed such an algebraic solver for this specific problem, the one that I show here. And it's actually the first fast solver for such a rather complex minimal problem, to the best of my knowledge, and that's the reference if you're interested. But let me go back to our result that I want to talk about here in this talk and look again at this catalog of minimal problems. We see, for instance, many interesting things here. One thing that is notable is that we see that all minimal problems involve at most 6 images. And so this means, in other words, there is no minimal problem that has 7 or more pictures involved. And so what we have done, we have not only identified all minimal problems, but we have also computed the number of solutions, which, as I said before, measures the complexity of each minimal problem. So it might be interesting for future projects to take a closer look at the problems that we found that have a rather small number of solutions marked in green. These might be good candidates to use in practice and to implement solvers for. On the other hand, we have also found problems with an enormous number of solutions, and for that guy up here marked in orange, we have not even computed the exact number of solutions since we gave up after several days of computing this number. Now let me tell you a little bit about the tools that we used. We derived and improved this catalog using algebraic geometry, which, as I said before, is what I do. Then to compute the number of solutions, we used Gröbner bases, which are symbolic computation techniques that are standard in algebraic geometry and commutative algebra. However, this only worked with a reasonable use of memory for problems with 2 or 3 images. For the problems with 4, 5, or 6 images, we needed to use state-of-the-art algorithms from numerical algebraic geometry, which are homotopy continuation and monodromy. But now I will not explain how these very cool algorithms work, which you can also develop these solvers. Instead, I want to spend my last minutes on explaining what we can say in the case of partial visibility. So in our previous catalog, we have assumed that all points and lines are visible in each given image, right? However, in practice, we might be confronted with situations where this is not true. Like in this example, image 1 does not see the black point, and image 3 does not see the black line, only image 2 sees everything. Such a situation can, for instance, happen because the detection algorithm failed, or because a point is literally outside the scope of one of the images. So hence, we want a catalog of minimal problems that also works for partial visibility. However, there are some issues with that. For instance, in our previous catalog, we had seen that minimal problems with complete visibility use at most 6 images. If we now deal with partial visibility, we can construct minimal problems for arbitrarily many images. So to provide a catalog, we need to restrict ourselves. In practice, we often, I'm not a computer vision engineer, but one often works with few given images, and the minimal problems with fewer images often seem to have less solutions, as we also saw in our table. So we decided to focus on the case where we have 3 given images. This is also because the case of 2 images is actually kind of easy. So 3 images is the first non-trivial and practically relevant setting. But now, even under this assumption, there is still infinitely minimal problems, and classifying them seems to be hard. So we restricted ourselves further to the setting where each line is adjacent to at most 1 point. We made this assumption for practical reasons because this is how the result of many detection algorithms looks that identify common lines on images. So, but even now, after all of these assumptions, there is still infinitely minimal problems. So this means we have to be clever if we want to classify them. And so what mathematicians often do in such situations is to put the infinitely many objects that we want to classify into finitely many boxes, such that all objects in the same box are related in the sense that if I understand one object in one box, that I then understand them all. And this is what we managed to do. We managed to put the infinitely many minimal problems into 74,575 boxes, formerly called equivalence classes. And since not all of them will be relevant for practical applications, we identified the ones that have less than 300 solutions. it turns out that there is 759 such equivalence classes. And here's a table that shows how many problems have how many solutions. And it's, for instance, interesting to see that most of these problems have 160 solutions. And finally, since many detection algorithms do not manage to detect incidences at all, we also classified the minimal problems in 3 views without any incidences. And there is 51 equivalence classes of such problems. Now I want to end my talk by showing you these 51 minimal problems without incidences. And I want to end on the final note that interaction between different sciences is key. We have heard this several times today, and I really believe, for instance, also our project is such a great example that shows how algebra, which is typically considered pure mathematics, can be successfully applied to computer vision. And also the other way around, like the problems we encountered in computer vision showed us aspects in algebraic geometry that need to be better understood and require more foundational research within the algebraic community. So I see interaction really as a two-way street that is beneficial for everyone. And so I'm very happy to be part of this interdisciplinary program. And I'm looking forward to many more interactions with different sciences and industry. Thanks.
Okay, thank you very much for this advertisement for WASP. That's I have some questions. Photogrammetry has been around for a number of years. How do these methods compare to traditional photogrammetry methods?
I'm not exactly 100% sure what photogrammetry here refers to, since I am not a computer vision engineer. I want to stress that.
Okay. Yeah.
But I guess, I mean, we are more like give like some sort of catalog of problems that you could develop solvers for. And well, the actual thing where you can develop solvers is that you can do this. And so this uses though very different methods than what has been done before. These monodromy and homotopy continuation. I'm not sure if that's an answer to the question.
Okay, so I'll try a different question, which is longer. Standard reconstruction using 2 camera angles and more than 5 points is bad because of real world errors and uncertainties. This you said. What about drawing each unique set of 5 points from a larger set of points, derive the solution each time, and then look at the distribution of the solutions to quantify 3D representation and its uncertainty?
So from my understanding, this is done what is classically done, that you have larger point sets and you draw 5 points and then you do it and then you repeat until you have some sort of point cloud. That's what I said at the beginning is what you do typically in the pipeline. But then sometimes, I mean, you might end up in situations where you actually do not have 5 points or you have lines involved or you have partial visibility. I mean, it depends a lot, I think, on your detection algorithm, if you can do that or not. And then the question is, maybe you can't do that. So, I mean, as I said, I'm not a computer vision engineer. I can only say, for instance, why I showed this picture with the dog and the cylinder and why they exactly developed the solver for that problem was because the idea was you have some sort of curve that could be like the movement of something. And then you want to sample points on this curve and also tangent lines like velocity vectors. And then you want to be able to solve a reconstruction problem. And then you can't do it with 5 points because I guess they didn't have 5 points. I don't know.